Welcome back, Marauders. This is video 5.6, Hess's Law. In this video, we're going to talk about using Hess's Law to find an enthalpy change. So we learned last time about using calorimetry to find the enthalpy change of a reaction. Remember, enthalpy change is the amount of heat energy gained or lost during a chemical reaction. And we're going to use Hess's Law to find that today. So enthalpy is a state function, which means it doesn't matter how you get from point A to point B. It just matters the distance between them. So if we have like point A and point B, we want to know the distance between these. Well, if we had a point C somewhere in between, and we knew how far it was from A to C, and then we knew how far it was from C to B, then we could find the distance from A to B. And that's basically what we're doing in Hess's Law. We're going to know the enthalpy change of two reactions, and those two smaller reactions will make up one bigger reaction, and it'll allow us to find the enthalpy change of that reaction. So basically you're adding up the enthalpy change of each step to find the enthalpy change of the entire reaction if it happens in two steps. So here's an example. This is a reaction between methane and oxygen reacting together to make carbon dioxide and water. So this is first showing how much energy is released when methane burns and produces water as a vapor. And then this is showing how much energy is exchanged when the water vapor turns to liquid and condenses. And so if we want to figure out the overall enthalpy change for this reaction, we can see that it's the 802 and the 88, both negative. So that means it's an enthalpy change of negative 890 kilojoules. Okay. So here's the same reaction. Probably how you're going to see it more frequently, just written out as reactions rather than as a graph like that. And so here you have the methane and oxygen burning to make carbon dioxide and water, and here's its enthalpy change. And here you have water, vapor turning into water as a liquid, and the enthalpy change here. And so if you add these two reactions together, you can see you'll have water vapor on the reactant side, water vapor on the product side, so they'll cancel out, and you'll get methane and oxygen as your reactants, carbon dioxide and water as a liquid on your product side. And so if we can add together the two reactions and get the third reaction, we can add together the two enthalpy changes and get the enthalpy change for the overall reaction. So that's a really simple example where the two reactions just add together to make the third. It's usually not quite that simple, and we'll see how to do that in a slightly different example next. So Hess's Law, you need to know two things. If the reaction is reversed, the sign of the enthalpy change is reversed or changed. So if you switch the place of the reactants and the products, if you flip the reaction around, then you have to change the sign. It has the same enthalpy change, but with the opposite sign. If it was endothermic, the reverse reaction is now exothermic, and vice versa. And then if the reaction coefficients are multiplied by some number, then so is the enthalpy change, right? So if you have twice as many reactants, you have twice as big an enthalpy change. All right, so here's kind of a typical example. We're given these three reactions, so these three we know the enthalpy changes for, and then it asks us to find the enthalpy change for this reaction. So we're trying to find delta H for this third reaction. So our goal is to add these three together and get this third reaction down here. Well, if we just add them together the way they are, we're not going to get this one. We're going to have to manipulate the reactions above just a little bit. So first thing, well, I see the OH right here on the product side, and right here we want to have it on the product side, so that's on the correct side. But right here the coefficient's a 2, we want the coefficient to be a 1. So this whole reaction needs to be multiplied by 1/2. We need to cut all the coefficients in half. And when you do that, you're also going to multiply the enthalpy change by 1/2. So this reaction up here at the top, I'm going to rewrite it after multiplying it through by 1/2. So you get 1/2 O2 plus 1/2 H2 makes OH, and then I'm going to multiply the enthalpy change by 1/2 as well, so it's 38.95. All right, so in our other parts of the reaction, we want to have monatomic oxygen on your reactant side, and just with a coefficient of 1. So we see where that is up here. We see oxygen monatomic right there, but there's a 2 in front of it, and it's on the wrong side. So what we need to do with this reaction is to reverse it. We want to flip it around, make the reactants the products the reactants. And we also want to change the coefficient by multiplying it by 1/2. So when we do that, we're reversing it, multiplying by 1/2. So that becomes oxygen on your reactant side and 1/2 O2 on the product side. When we do that, so we reverse the reaction, we need to change the sign. It was positive, it's now going to be negative. We multiplied all the coefficients by 1/2, so we'll multiply this by 1/2. It'll be 247.5. And then lastly, when we add these together, we want to get monatomic hydrogen on your reactant side. Here it is on the product side with a coefficient of 2. So we'll need to take this equation and reverse it, multiply it by 1/2, so that the hydrogen ends up over here on the reactant side. And then on my product side, I'll have 1/2 H2. Since I reversed the reaction, I changed the sign, so it becomes negative. I multiplied all the coefficients by 1/2, so I'll multiply this number by 1/2, and so that will be 217.95. And so now I'm going to add these three reactions together. So what do we have on the reactant side? We have 1/2 O2 plus 1/2 H2 plus O plus H. So that's everything that's over here on the reactant side. And now everything on the product side, OH plus 1/2 O2 plus 1/2 H2. All right, now if there's anything that's a common factor, we can cancel it out. So we have 1/2 O2, 1/2 O2, 1/2 H2, 1/2 H2, and then what's left when that stuff was canceled out is just oxygen plus hydrogen makes OH. And so since these three equations added together gives us this equation, then the delta H's for these three equations will give us delta H for that last equation. And so we'll add these together. And when we do that, we get negative 426.5. And so that's Hess's law. It's using reactions that you know the enthalpy change for to find the enthalpy change of a reaction that you don't know. We saw here how we reversed some of the reactions, multiplied by some coefficients in order to make these three reactions add together to get the fourth. And even though this reaction may not happen in those steps, as long as the reactions add together, then we'll get the same enthalpy change.